Okay, today we're looking at topic 7.7, part 2. We're still calculating equilibrium concentrations and using Rice tables, but now we're going to focus on what happens if we already have an equilibrium constant and how we proceed to fill out our table. So Rice tables are used to find the concentrations of chemicals at equilibrium when the equilibrium constant is known. So we can fill out this bottom line if we know the equilibrium constant. These tables involve the use of a variable as a placeholder. Then, when the equilibrium expression is used to find the variable, and then concentrations or pressures of our chemicals can be found. So it's a little bit longer, a little more steps than our previous ones, but still really doable. So first thing I will point out, there is a typo here. Yours says gas. This is supposed to be a solid. So you make that note there. So at 218 degrees Celsius, the equilibrium constant is 1.2 times 10 to the negative fourth. So that's one thing that's going to be a little different here. You're given your equilibrium constant. And then for the equilibrium below, calculate the equilibrium concentrations for each chemical if a sample of NH4SH is allowed to decompose and reach equilibrium. So this is a solid, and at this temperature, it starts to break down, decompose, and makes ammonia and hydrogen sulfide. So when we have a solid in our table, we haven't really dealt with these yet. The first thing we can do is cross out our column for the solid. Solids are not included in our equilibrium expression, so they are not actually something we need to calculate in our Rice table. So now we can go from there. If we introduce this chemical only into our container, we're going to start with 0 of the products. Then it's allowed to reach equilibrium, so some of this is decomposing and it's forming some of our products. Now we don't know how much, so we're going to use X as a placeholder to give us a variable. Now we're gonna have X still follow that mole ratio for this line. Okay, that's our important part. So we've got a 1-to-1 ratio. We are adding on the right side because we've started with 0, so we need to get more of it to get to our equilibrium. And we're just going to add X, just one X since they're coefficients of 1. So your X just matches your coefficient. Then we can solve from there. So we're at 0 plus X gives us X. 0 plus X gives us X. Pretty straightforward. Now, what we typically do from here is we write our equilibrium expression and then start plugging things in. So that's exactly what we're still going to do. Our equilibrium expression is our concentration of our products, so NH3 times our concentration of H2S. And we don't need to divide by our reactant because it is a solid. We're going to leave that out. Now we're going to plug in what we know into this expression. Now, we already have a value for Kc, so 1.2 times 10 to the negative fourth is going to go on the left. Each of these we're going to replace with our value at equilibrium, which is X. Remember, this is where we can calculate K. So we're going to put an X and an X for both of those chemicals. Well, we can simplify that. We can say 1.2 times 10 to the negative fourth is X times X, or X squared. And we just want to continue solving for X. So from here, to get X isolated, we would square root both sides of our equation. I like to do that in a different color so we know what's happening. So X is going to equal the square root of 1.2 times 10 to the negative 4. So we've got our square root button here. So second and then your square root. 1.2 times 10 to the negative 4. And we get 1.095. We get a very large number times 10 to the negative 2. Now we do want to stick with our significant figures. So only 2. So this will round to 1.1 times 10 to the negative 2. Now, here's the key. We haven't finished our problem. We have not stated what the equilibrium concentrations for each chemical would be. So that's how we're going to finish this question. We're going to say the concentration of NH3 is equal to X, which is equal to 1.1 times 10 to the negative 2 and it's a concentration, so we're going to put molarity. And that is the same for H2S in this case. It's equal to X, which is equal to 1.1 times 10 to the negative 2 molar. So here we're using our equilibrium constant to help us figure out what the concentrations are at equilibrium. So we're kind of working backwards from what we did before, where we had the concentrations and we found K. Now we have K and we're looking for the concentrations. So taking it a step further. All right, let's take a look at another example. So things to keep in mind as we do these, your coefficients should match your coefficients on your X. If we have a solid or liquid, pure liquid, we can cross it out. And we're going to be doing some solving with our equilibrium equation, or equilibrium expression. So let's look at our next one. Get us all set up. So we've got nitrogen and oxygen gas combine when burned to form NO gas according to the reaction below. A gas chamber initially contains 1 atmosphere of N2 and 1 atmosphere of O2. So we can plug those in. Those are initial, in this case, pressures. So we might make a little note that everything's in atmospheres. That might help you later in terms of labeling units. If the equilibrium constant Kp for the reaction is 4.16 times 10 to the negative 4th, determine the partial pressure of each gas at equilibrium. So we need to know the pressures of our gases down here at equilibrium. So we're going to fill out our table the best we can. So we have initial concentrations of our reactants. We have none for our product. So since we would be our reaction would be shifting to the right to give us product, we're going to add on the product side and subtract on the reactant side. And then we're going to use X's as our placeholders, and we're going to make them match our coefficients. So we have 1 nitrogen, so just 1X, 1 oxygen molecule, so 1X, and 2 NOs, so 2X. And then we're going to do our math. We've got here 1 minus X and 1 minus X. And then here we've got 2X. So we just fill out our table with our X values. Now we're going to start with our K expression, in this case Kp. So it would be equal to the pressure of NO squared over the pressure of N2 and the pressure of O2. And we can plug in, we've got Kp, so we're going to put that on the left, 4.16 times 10 to the negative 4th. And then our pressure of NO is 2X. I'm going to put that in my parentheses still because that whole thing is being squared, so I want to keep track of that. And then on the bottom, we've got 1 minus X for each of these, and we're multiplying it by the same thing. So I'm going to write it as 1 minus X squared. That's just an easier way of writing it instead of writing it twice, since it's multiplying. Now, this may look really ugly, but we can start by simplifying it pretty quick. We've got squares on the top and bottom, so we can square root both sides of our equation and simplify things. So let's see what that does. On the left, it's going to square root our number. So the square root of 4.16 times 10 to the negative 4th. And we get quite the number here. So 2.04 times 10 to the negative 2nd. And these, the square root is going to cancel our squares. So we're going to have 2x on the top and 1.00 minus x on the bottom. All right, still not pretty, but doable. So I'm going to simplify things next by multiplying both sides by 1 minus x. I'm going to run out of space over here, so let's just do it there, minus x. Okay, and then I'm going to go ahead and simplify that. So I've got 2x on the right side. Actually, I'm going to move that over. Let's do the left side first, so we've got plenty of space. So here I've got 1 times 2.04 times 10 to the negative 2nd, so that's 2.04 times 10 to the negative 2nd. And then I've got minus x times that same thing, so 2.04 times 10 to the negative 2nd x. So as my variable, I'm going to make it extra obvious so I don't lose it. And that's all equal to 2x. Okay, now I want to get my like terms together, so I'm going to add my 2.04x to both sides. So on the left, I get 2.04 times 10 to the negative 2, just bringing this down. And then I get 2 plus 2.04 times 10 to the negative 2. And we get 2.0204. And that has that x at the end, our variable. And I didn't round this because I want to make sure that I'm kind of keeping things consistent throughout, and then I'll round at the end. 2.02 times 04, divide on both sides. So my x value equals 2 times 10 to the, 2.04 times 10 to the negative 2 divided by 2.0204. We get we've only had 3 significant figures on all this stuff, our 1.0 are given values. So 1.01 times 10 to the negative 2. We could also write it as 0.0101 if we wanted to. Either way is valid. Now, again, we're not done. This is the key part. We still got to report our answer. So we are looking for the partial pressure of each gas at equilibrium. So we want to report what they are. So my pressure of N2 is actually going to be the same as my pressure of O2. So I can put that they're both equal to each other and that they're equal to 1 minus x. And then I'm going to solve that. So I'm going to put in my x value for this and solve that. So I've got 1 minus 0.0101. I'm going to take it out of scientific notation. So I get 0.9899. And our sig figs, we've only had 3. So 0.989. This would bump. So 0.990. Here we go. Now it is pressures, and our initial stuff was in atmospheres. So we're going to put atmospheres on there. And then our other one is our pressure of NO. It's equal at equilibrium to 2x. So 2 times our x value will give us 0.0202. That gives us our 3 sig figs, atmospheres. And that would be our final answer there, these values. All right, so that's the key thing here is our goal is not just math, right? This is chemistry. So our goal isn't to solve for x. Our goal is to solve for x and then use it to answer the question, which is what are those equilibrium pressures? Okay, let's try one more. Flip your paper. Go here. So our last one here, so it says calcium iodate dissolves when with a KSP. So we haven't seen that subscript much yet, KSP. We're going to deal with it more later in the unit, but it is called solubility product. So basically it's what happens or what the equilibrium is when something dissolves. All right. So determine the equilibrium concentrations of each ion. If excess calcium it should say iodate. Iodate is dissolved in to create a saturated solution. So it's not sulfate, it's iodate. All right. So we do have a solid here, which means we get to cross that part out. I love that because it simplifies our expressions a little bit. And then it doesn't give us any concentrations of our chemicals to start. We're starting with solid and it's dissolving. So we're going to be shifting to this side. So we're going to be adding x on this side, and we're going to make it match the coefficients 1 and 2. So adding x, adding 2x. So we get x and 2x for this one. All right, now we want to start plugging into our expression. We do have our KSP value. So KSP would be equal to our concentration of our calcium ion times our concentration of our iodate ion squared. So we're going to replace KSP with its value. Oops. 6.5 times 10 to the negative 6th. Our calcium is going to be X, and our iodate is 2X, and then I'm squaring. So I do this, I put it in parentheses because I want to make sure I'm squaring this. Here's what I see many students do. They write 2X squared, and then they don't actually do the math here. What's actually happening is the 2 is squared and the X is squared. But if you write it like this, you'll forget to square your 2. So be really careful with that. So let's start simplifying things. Why don't I want to write a 5? We get X times 2X squared is 4X squared. So then if I simplify that one step further, I get 4X cubed. Right? So many times that 4 is lost. So be very careful with that. Okay, to start simplifying this, we can divide by 4 on both sides. So we get X cubed equals 6.5 times 10 to the negative 6th. And we're dividing that by 4. So we get 1.6 times 10 to the negative 6th. Now, I'm going to leave this number in my calculator because I'm not quite done. And we want to go ahead and finish this out and find X. So we need to do that by taking a cube root of this. Now, if you're not familiar with how to put in a cube root, here's the easiest way. Taking the cube root of something is the same as raising it to the 1/3 power. So here's what I do. I'm going to leave that in there, and I'm going to use my caret key up here to raise it to the 1/3. So I put it in parentheses so I know it's doing it right, power. And that gives us our cube root. So your X value equals 1 point, and we have all of this. We're going to go ahead and round it. We've got 2 sig figs, so 1.2 times 10 to the negative 2 is our X value. Now again, we're not done. We want to report our answer. So our answer is the concentration of calcium and the concentration of iodate at equilibrium. Calcium is X, so that's going to be 1.2 times 10 to the negative 2 molar. And iodate is 2X, so we're going to take that, 1.2 times 10 to the negative 2, and multiply it by 2. And we get 2.4 times 10 to the negative 2. You'll notice it only really multiplies that first part because it's such a small value. And that is our final answer. So if we took calcium iodate and put an excess of it into our container, so we'd still see some solid at the bottom, this is how much would actually dissolve. All right, pretty small molarity. So that's telling us that it's not super soluble. It doesn't dissolve that much. So that's going to be something we're exploring towards the end of the unit a little bit more, but this is a good little preview because the skills are transferable. This part doesn't change. What we think about the numbers is what we apply later. So you've got a couple of practice problems, 2 on this page and then 3 more on the back. You'll need to write your ICE tables. Remember if it has a solid to cross those out, get rid of them, and then after this you'll tackle your mastery chart for it. All right? Thanks, guys.